one today. I have known Amir for a number of years when I was a graduate student, but I think Shankar was sending me an email and said, I know Amir since he was a graduate student with Moti Hybloom, and you were the first graduate student. So that's something I learned during the weekend, as usual from Shankar's emails. Again, I won't go to details, so thank you for being here. 4 p.m., the usual place, usual time, room 2117. I got the cheat sheet. Thanks for coming again. This is your. Okay. Well, thanks, Mohammed, for inviting me and giving me this opportunity to tell you a bit about the work we've been doing to expand the toolbox of quantum sensing techniques to explore quantum materials. And before I dive deep into the subject matter of today's talk, which will be looking at spin excitations in solids, I want to give a little bit of a broad motivation for why developing new tools for exploring materials, I believe, is something that we should be doing continuously. I'm going to give just a handful of examples. So this is by no means comprehensive, but starting from ground state properties, I have here two examples. One is a quantum spin Hall insulator. This is a topological insulator. It's a 2D quantum well here that under certain conditions is insulating in the bulk, but because it's topological, it has edge states, and these edge states are carrying current. As you can see, these are counter-propagating edge states, so there is no net charge current at the boundary of the sample, but because each edge state is carrying opposite spin, this edge state actually in steady state is carrying a spin current. And it's a steady state spin current. And today, up to date, we don't really have any tools that can detect the presence of a spin current in steady state in this material. So this is the question, how would we detect the existence of this spin current? Another example is shown here. This pink layer is a monolayer of graphene that we made a couple of years ago. And under certain conditions, in fact, in the presence of very strong magnetic fields perpendicular to the layer, the system is predicted to develop a canted antiferromagnetic state where on one sublattice spins are pointing in the plane in one direction, on the other sublattice of graphene they're pointing in the opposite spin direction. Now we do have quite a few techniques that are capable of detecting spin order in solids, particularly neutron scattering, but what is unique here is that this layer is just one monolayer, and the magnetization or staggered magnetization density in this material is at least 1 million times smaller than what you would find in a normal antiferromagnet. And so neutron scattering simply does not have the sensitivity to be able to detect this kind of order. So we really need new tools in order to be able to study the underlying order in the ground state, for example, of mesoscopic systems. Now, going above the ground state, we actually have quite a few interesting systems that have excitations that are quite unique. And here again, just two examples. One are spin liquids. This is something that you've probably heard about. These are highly frustrated magnetic systems where the ground state doesn't want to order magnetically in the conventional forms, namely ferromagnetic or antiferromagnetic. But it's predicted to form this very, very highly entangled ground state where every pair of spins form a singlet, and the ground state is a superposition of all these possible configurations. But above the ground state, this system has excitations. In fact, these excitations are spin excitations, or one of the type of excitations that exists are spin excitations. They do not carry charge, so we won't be able to detect them through electrical means. And in fact, their statistics is fermionic. Unlike most spin excitations, and I'll talk a lot about spin excitations today, these excitations are fermionic and not bosonic. And again, we really lack proper tools to be able to just detect the spin properties of these systems uh, when they're decoupled from charge. Another example are excitations of very isotropic magnets, Heisenberg magnets. These are called merons. These are topological excitations where the texture of the excitations form these type of vortex-antivortex pairs. And again, here we'd like to have some evidence for their existence, something that could tell us that indeed these type of excitations exist. And one of the studies that I'll talk about today was motivated by the search for merons. We didn't find merons, we found something else, and I'll tell you more about that a bit later. And finally, once we have long-lived excitations, and these could be very peculiar and bizarre excitations, as I described before, but if they're long-lived, one can describe a chemical potential associated with them and gradients of chemical potential associated with these excitations, and then the transport of these excitations. So again, since these are spin excitations we're talking about, we lack the tools to perform full transport characterization of these spin excitations, again, because they're decoupled from charge. And here again, just two examples. One are thermal properties of spin excitations. So now they're carrying heat. As you can see from the title here, superfluid spin transport. So under certain conditions, spin excitations can form superfluids, and we'd like to be able to study their transport characteristics as well. So overall, we really would like to develop new tools, and we've been doing a lot of tool development in my group over the course of many years. And today I'll talk about the use of a specific technique, one that uses NB centers to study magnetic fields, and we'll focus on thermal spin excitations and emergent spin excitations that appear in certain magnetic systems. And please interfere or interrupt with questions so that I'm not completely disconnected from the audience. So the technique that we're going to be using is a nitrogen vacancy center magnetometry. It's a very well-established technique. It started about a decade ago when pioneering work from Germany were able to isolate individual NB centers and study its characteristics. The reason it is very useful is that the ground state property of this defect, which sits inside diamond, it kind of lives in between the valence and conduction band of diamond, has a very, very simple energy spectrum. It's a three-level system because it comprises of two holes of the basically full shell of this defect. And the evolution of the levels of this ground state configuration is an MS equals 0 state that is magnetic field independent, and then two excited states that evolve with magnetic field according to G factor of 2. There's an interesting zero field splitting here that comes from spin-orbit interaction inside the solid. But overall, for the purpose of this talk, we're going to just be using this NB center as a two-level system in which we're going to be able to harness its properties and its coherence to detect magnetic fields. Now, there are several key interesting properties of this NB center. One is that when you shine light on it, it cools itself down to the ground state. So even if you do an experiment at room temperature, and the level spacing here is far, far below room temperature, nonetheless, this NB center could be initialized and prepared into its ground state with very high fidelity. It is doesn't care about temperature, so this technique works really well at any temperature that you choose. And we can do fluorescence readout of the spin state of this NB center to determine whether it's in the ground state or one of these excited states simply by the amount of photons that it emits when we shine green light on it. And finally, for the purpose of this talk, the spatial resolution of this technique, because this defect is atomic, it measures magnetic field on an atomic scale. If we're able to bring this NB center close to a material of interest, our spatial resolution is dictated by that distance. This is not the case generally. One could, in principle, have a far better spatial resolution, just like in an MRI system. The magnets, the coils that detect the magnetic field of the nuclear precession are sitting maybe a meter away. The spatial resolution is nonetheless a fraction of a millimeter. So there are ways to get spatial resolution better than the distance, but for everything I'll be talking about today, spatial resolution is dictated by the distance to the sample. And in fact, this will be a very important parameter that governs the kind of physics that we're extracting. Yeah.
Basic question. I mean, this initialization, since splitting is much small, energy scale is much smaller than temperature, is it special to initialize the ground state, or can you initialize in any of those spin states?
So the mechanism, just the radiation and relaxation processes initialize the NV center in the ground state, the MS equals 0 state, from which you can prepare your NV center into any of the excited states by basically driving an RF signal and flipping it to the desired state. So you can prepare it in any state you like, but the optical relaxation pathways lead you to the ground state.
Despite the fact that the energy scale is much smaller than temperature, that seems counterintuitive.
Yeah, it's conservation of angular momentum that has to do with it. So the two excited states have ms equals plus and minus 1. The ground state is ms equals 0. That plays an important role. That selects the ground state. So how do you use a two-level system for sensing? You need to satisfy 3 criterion to be able to initialize it, to reliably control it, and then detect in which state it is. And these criteria are satisfied with the NV center. Here I depict the block sphere of the NV center of a two-level system. The north pole, let's say, is the ms equals 0 state. South pole points to the ms equals minus 1 state. And our control are just RF pulses at a frequency given by the level separation, allowing us to prepare a superposition. And then, in the presence of an external magnetic field that we'd like to detect, this phase, this superposition, acquires a phase, and that phase depends on how long we let the system evolve, and that time is given by the coherence time of the system, so the time it maintains its memory. Our detection allows us to say something about whether it's in the ground state or in the excited state, but every single measurement, because it's a quantum measurement, has an uncertainty of pi. So we don't really know which one, and we need to improve that uncertainty in phase by repeated measurements. So one could do a simple analysis to see what the signal to noise is in the system, and it's easy to see that for a given coherence time, T2, and number of repetitions that we can acquire within, let's say, 1 second, this is the signal that we'd be able to measure. And just typical numbers here for coherences of about 100 microseconds. The sensitivity of a typical NV center would be in the range of 10 nanotesla. And just to give you a sense, if I'm sitting, let's say, if I'm sitting 10 nanometers away from an electron spin, the magnetic field generated by that electron spin at 10 nanometers is about a microtesla. So we should be very easily able to detect that field. And the field generated by a nuclear spin is on the order of a nanotesla. So we need to work a little bit harder to be able to see a nuclear spin. But all of that has been already demonstrated. Yeah. Of course. So if you can't collect the photons emitted by your NV, then you're going to obviously not be just limited by these considerations. There are going to be additional considerations that you need to worry about. Yeah.
And if you wanted shorter times, how does that degrade? How do you noise? So what is the shortest time you could measure? Time scale. Like the minute it is fluctuating.
Yeah, so you can, okay, so the shortest time has to do with a single kind of shot, basically initialization, evolution, readout. That's on the order of a few microseconds. Yeah. Now, the way I've depicted how to measure magnetic field before was basically letting the phase evolve and then reading out the spin. Of course, you can do much more sophisticated things like echo experiments, which allow you to measure magnetic fields that are not static, but are fluctuating. You could either measure coherent fluctuations or just noise. And generally, there is a very nice formulation that relates the way the coherence of the NV decays over time with the pulse sequence that you drive it. And basically, each one of these pulse sequences corresponds to a filter function, some bandwidth that you can dictate or select a priori off of your noise curve, so you can pick out specific bandwidths or sections of the full noise characteristics of your environment. Now, since we're going to be talking about solid-state systems, I want to point out that this coherence time T2 in relation to a material that is sitting nearby will be directly probing the imaginary part of the susceptibility of that material, which then leads to the relaxation of the NV center. So this is a very important relation generated by the fluctuation dissipation theorem. You can really see that the dissipation of the NV center is directly related to the fluctuating component of the environment. And you see that there is a momentum and frequency component to this susceptibility, and I'll talk more about which frequency and what momentum are we probing when I come to talk about the experiments themselves. Yeah?
That always expect the material to be in thermal equilibrium?
It doesn't have to be. Here I'm basically showing what happens when it is. So this is when it is, yeah.
Is like magnetic, is basically total susceptibility, like current plus spin, right?
So this is, so remember, what the NV center is responding to are magnetic fields along its axis. So this is a susceptibility associated with magnetic fields generated along the axis of the NV center.
Sorry,
Yeah.
K over there as well. So is that integrated over?
So if you can do an experiment that is case specific, and you'll see. So we are going to have a bandwidth in K and a bandwidth in frequency when we're probing a particular magnet coming soon. All right. So over the years, we've been perfecting this technique. We've turned this technique into a scanning probe. These were the original probes that we've made, starting out from a bulk piece of diamond. You thin it down to a slab of a couple of microns, and then you etch from the other side to form a pillar. So this is all part of one diamond matrix. At the end here, there sits one NV center that basically radiates light through the tip, through the waveguide, up into our microscope. And we can integrate our drive electronics as well. What you see here are the newer versions. They look uglier, but they're much easier to make. Much thicker, but still one pillar. And at the end of each one of these pillars sit just a single NV center that we now can scan around and extract the local magnetic fields. Now, in this talk, I'll be using both this local technique, but also a fluorescence method that relies on ensembles. So when we don't care that much about spatial resolution, you can imagine having a slab of diamond that has many, many NV centers, and we place a material of interest on top of it. And now our spatial resolution is given by our optical spot, roughly 400 nanometers. And to put NV magnetometry into context of other techniques, I've plotted here sensitivities, or where various techniques are kind of useful on a map of wavelength and energy. So neutron scattering that I mentioned in the beginning can go down to very short wavelengths, but on the other hand, they are typically kind of get saturated once you try to take them to very low energy. So typically below a millivolt becomes really hard. You have a lot of optical techniques where you're sensitive to wavelengths in the micron range. And of course, more modern techniques using circuit QED, these can go to very low frequencies, very sensitive, but very long wavelengths, because the wavelength of the radiation is just very long. And you see NV centers has a nice corner in parameter space, both short wavelengths, because it can approach a sample very well, and can go down to low frequencies. Today, I'll talk about fluctuations in a system in the range of a few hundred kilohertz to gigahertz. Okay, so I'm done with the introduction, and now I'd like to dive in and tell you about the fact that magnons can form superfluids. I've already alluded to that in the introduction. And I'd like to show that using NV center, we can actually measure spin chemical potential, which is a stepping stone towards doing real transport experiments with spin excitations. And we can detect something that is known as second sound. You might be familiar with second sound from liquid helium. And it's basically an emergent excitation of the thermal excitations that exist in certain magnets. So I've mentioned already spin superfluids, and it sounds like a very hot and new topic, but in fact, it's a really old, but not very well studied topic. This is a seminal paper from Bert Halperin and Pierre Hohenberg, 1969, so this is, what, 60 years ago. And the title is Hydrodynamic Theory of Spin Waves, and the first sentence reads, a hydrodynamic theory of spin waves is developed for certain magnetic systems in analogy with the derivation of two-fluid hydrodynamics for liquid helium. So these gentlemen, already 60 years ago, realized that certain magnetic systems, and in fact, there are many magnetic systems, so these are not that kind of rare, that can be thought of and described in terms of a two-fluid model associated and basically analogous to superfluid helium. So what are these two fluid components? So in a two fluid model of helium, we have the condensate, which has a global order parameter, and we have excitations that live above it. These are broken pairs, if you like, that basically live above the condensate. And it's the interplay between these two that give us a lot of the physics, like the fountain effect and many other things that exist in liquid helium. And in fact, a lot of these things are present in magnetic systems where the underlying condensed phase is the magnetization itself. It is a complex amplitude. It has a well-defined amplituded phase. It's global. And above it, we have spin excitations. These are the spin waves. And I'm just depicting here just a simple example of spin waves. These are exchange-coupled spins. So I have a lattice of spins. They're pushing on one another, and these generate waves. And these spin waves have a spectrum, a dispersion. If it's only exchange-governed, it will be quadratic. And there's an interesting spin gap in the system that's given by the anisotropy in the system. And the spin gap here is given by, if it's a magnetic field-driven anisotropy, is just given by what's known as Kittel law, and it starts out as a square root in magnetic field. And I want to point out that these spin excitations can live only above the spin gap. So once I have an isotropy, or let's say a magnetic field, there's a minimum energy associated with creating an excitation. You can easily see that tilting the spins away from the applied magnetic field, or the anisotropy, costs energy, and that's the spin gap. So all these spin excitations live above the gap. And typically their frequency is going to be very, very high in the gigahertz to many, many gigahertz or terahertz range. So what I'll be focusing about is the dynamic phase for now, these spin excitations. And as we know, these spin excitations are bosons. And if we could increase the number of excitations, we should ask, well, what might we expect? So we know in a bosonic system that as we increase the number of excitations, the chemical potential will eventually rise. But once it hits the bottom of the dispersion, it's going to basically settle, because now we can have macroscopic occupation of the ground state. This is a property of bosonic excitations, whereas for fermionic excitations, the chemical potential would increase continuously with density. So this would be a signature of the thermal excitations in the system if we could increase their number and if we had a way of measuring the chemical potential. And I'd like to argue that we have, using an NV center, we can directly measure what this chemical potential is. And again, it relies on the fluctuation dissipation theorem. If I prepare my NV center at the ground state or any one of these excited states, fluctuations in the magnet at the frequency of the two-level system would lead to relaxation. And that relaxation is therefore a measure of how many of these fluctuations exist at that particular frequency. The number of fluctuations is, of course, described by a Bose distribution. It's characterized by a temperature and by a chemical potential. And I won't explain why, but we have a way of knowing that the temperature in the system is unchanged as we're filling it up with more and more spin excitations, and we're just changing the chemical potential. And so it turns out that the rate is given by complicated things, right? So not only the distribution, but also the density of states, etc. But if we could do a ratio experiments, we could compare the rates under two conditions, then all the complicated physics drops out, and the only thing that's left is the contribution due to the Bose distribution. And so we're going to do two experiments. One is measure the relaxation of our NV spin in equilibrium, and the other is when we're filling it up with a lot of spin excitations. And I'm not telling you how we fill it up, but there are many different ways of driving the magnet to excite it more, either by radio waves or by spin injection using spin Hall effect. But we can pump magnons into the system. Yeah.
I'm worried about magnetic anisotropy here. You're going to talk about it like it so far it seems like you're treating it like a Heisenberg magnet.
So these experiments are done in YIG. It is fairly isotropic on the scales that we're interested in. Obviously, there are going to be some crystalline anisotropy, but we are kind of at energies that are far greater than these anisotropies. Yeah. All right, so this is the outcome of the experiment. Vertical axis is chemical potential as extracted by the ratio of these two rates and just one experimentally extractable parameter, which is the level splitting of my NV center that I know by other means. So it's a very, very simple relation relating relaxation rates to chemical potential. On this axis is the magnetic field. Remember, magnetic field is controlling the spin gap in the system. And on this axis is somehow our way of pumping magnons. So it's the number of magnons. It's not a calibrated axis, but nonetheless, it is increasing as we go to the right along this axis. And what you can see is that the chemical potential indeed rises, but it always saturates, as we expect it to. It saturates. And note that it saturates precisely onto this black curve, which is the minimum of the dispersion. It's basically the top of the spin gap. So this is kind of a very nice and strong confirmation that, number one, we're able to measure chemical potential in the system of spins. There is no charge associated with anything here. And we're able to see how the chemical potential saturates, suggesting that this system is now condensing into an additional condensate associated with the minimum occupation here of the minimum energy state. Yeah.
So I think the underlying assumption you mentioned is that you assume it's that these magnons are governed by Bose distribution. That
Yes.
The system is thermalized.
So the system is thermalized, and we know that it's thermalized by measuring its temperature using, again, NV centers and how it's in contact with a thermal bath, with a phonon bath in the system. But even if it's not in thermal equilibrium, the excitations of this magnet are bosons.
No, that I agree, but if I want to make sure that it's thermalized, I either have to show like fluctuation dissipation theorem, or I should fit it with the Bose distribution. Because naively, I would say, well, if I'm driving it harder and harder, at some point it should saturate. So the saturated per se.
So this is, yeah, so remember, you're thinking of this as really driving the system. We're pumping spins.
Exactly.
We're just pumping spins. We're increasing the number of particles in this system beyond what it likes to be in equilibrium. So in equilibrium, in a Bose system, chemical potential is 0. And temperature is whatever the temperature is. So we're pushing the system out of equilibrium, maintaining temperature, but just pushing its chemical potential. Now, it's true, if I didn't have a Bose distribution, then I wouldn't get saturation at this value. I would get something different. And there have been experiments by Tuno, van der Sar in Delft, for example, that shows that you can deviate from this type of saturation if you're driving the system indeed into a distribution.
Is it possible to, since we have frequency selectivity, is it possible to show that it's actually thermalized and it follows a Bose distribution?
It's not so easy because the way I tune my spectrometer And in what I've explained so far, it's not so easy because the way I tune my spectrometer is I can change this energy level to measure different energies, population of different energies, but I'm also affecting the magnet at the same time. There are techniques using AC Stark effect where you can keep the magnetic field fixed and now probe the NV center at frequencies that deviate from the resonant condition, going off resonance, and that's something that we're doing a lot right now. Yeah. Okay. So far, we've talked about the thermal phase. We've talked about the number of particles in the system that we can basically condense them also. Note that this condensate is different from the static phase that I described before that Halperin and Hohenberg are talking about, which is the magnetization. That is something that is there in the absence of drive. And what I'd like to talk now is about low energy excitations, and can the system have any fluctuations below its spin gap? And from what I've told you so far, no, it can't, because all the excitations live at frequencies above the spin gap. So the question is, can there be something that is fluctuating in the system at frequencies that are far below the spin gap, or this is forbidden? For this study, we're going to be looking at a material called chromium trichloride. It's a layered magnet, and in the beginning, I'll talk about a monolayer. It's a layered antiferromagnet, so each layer consists of magnetized spins in the plane, and when you have multiple layers, this below a certain temperature, this magnetization becomes staggered, and each layer has a magnetization that's pointing in the opposite direction to the other layer. But we're going to be starting just with a single layer, so it's a ferromagnet. And we're going to use this kind of imaging of ensembles to look at what is going on. And we're going to start with a static phase. The static phase, as I mentioned, is the magnetization itself. So we can just pick out what the magnetic field generated by our monolayer is. And you can see that there is some signal appearing once you're below the ordering temperature. And if you take a line scan, you see that going from 15 Kelvin down to 6 Kelvin, indeed, the system builds up some magnetization. That's the static component, and we can plot it and see how that magnetic field that we're picking up depends on temperature. You see there is an onset that starts roughly at 15 Kelvin. That's the ordering transition of the monolayer. And we can fit a line here that agrees really well with the linearized spin wave model, which allows us to extract the exchange interaction for this magnet and compare it with the literature, and we're getting numbers that are very consistent. So this is just the static magnetization of the system, and it's ordering very nicely at around 15 Kelvin. But what I like to do is to explore very low frequency excitations. And as I mentioned to you before, the zero field splitting here is a couple of gigahertz. I like to measure fluctuations at frequencies that are much, much below. And so we're going to resort to these echo sequence techniques, which for each pulse sequence corresponds some filter function that allows us to extract frequencies of fluctuations that are dictated in this particular example by a bandwidth, which is given by 1 over the evolution time. So if my evolution time is 10 microseconds, then the bandwidth here, I'm going to be picking up fluctuations at around 100 kilohertz, well below the spin gap. So you might say, well, I shouldn't see anything at this frequency because all my fluctuations due to spin waves are at very, very high frequencies. But nonetheless, this is what we're picking. Remember this formula, imaginary part of susceptibility. So this pulse sequence places omega here to be around 100 kilohertz. What about the spatial dependence? So it turns out that if my NV is sitting a distance d from my magnet, and I characterize the excitations in my magnet with a wavelength of magnetization. So this is a wavelength that's infinite. So it's a uniform magnet. It turns out that the magnetic field generated by a uniform sheet of magnetization is 0. And it might contradict your expectations, but it's a fact, and we can talk about more in the break. But there is no magnetic field generated by a very large sheet of magnet The only magnetic fields you're going to be picking up has to do with the boundary of the sample. But if you're very far away and this distance is small compared to the distance to the boundary, you're not going to be picking up any magnetic fields. You can ask, well, what happens if my magnetization is like an antiferromagnet? So every second spin is flipped. It turns out that this now is generating magnetic fields, but because this oscillation of this magnetization, its wavelength is so much shorter than this distance, we're also not going to be picking up anything. And we're going to be picking up magnetization optimally, whose wavelength is given by the distance to the NV. And that's, in fact, the filter function that you can calculate for any wavelength of magnetization. You see it goes to 0 when k goes to 0, and it's exponentially small when k is large, and it's peaked at a distance 1 over at d. And so we have also a filter in momentum that this NV is sensitive to. And our NV in the experiments I'm going to show are about 50 nanometers away. So this is our k 1 over 50 nanometers. Okay, so now we know that we're looking at the susceptibility of our layered magnet at a well-defined k and omega shown here. And we don't expect to see much because we're at very low frequencies. And this is what we find. So this is 1 over T2 within the wavelength and frequency bands that I described. And what you see is that, again, starting from 15 Kelvin, where the magnet orders, number one, you see a very big peak having to do with the critical fluctuations of the system as it undergoes its transition to a ferromagnet. But below that, there's something really surprising. So number one, there are fluctuations. And number two, they're becoming stronger and stronger as you cool the system down. Now, that is very counterintuitive. You expect that as you cool things down, there are going to be less fluctuations and the system will become quieter. But in fact, that's not the case. And a magnetic field doesn't change the picture that much. And this was, for us, a very important observation because it told us that mesons, which I mentioned early on in the introduction, are not the cause of these fluctuations because mesons would not be able to survive at these magnetic fields. They become very unfavorable at these kind of magnetic fields. So what is going on? We talked about the spin gap and we talked about the excitations. They all have frequencies above the spin gap. And these are called transverse excitations. These are the magnons, the spin excitations in the system. But what we didn't talk about are fluctuations in their number. So what we are seeing are actually fluctuations in the number of magnons and not the magnons themselves. And this, it turns out, can have very low frequency fluctuations. And in fact, if I think of the soup of magnons, the collective body of magnons, they could behave in very different regimes depending on their scattering rate with respect to one another. So just like electrons, when you're in a solid, you will have various momentum relaxing events. These could be either interactions with impurities or with the boundaries of the sample or phonons. But nonetheless, if the rate of relaxation of momentum is faster than the interaction rate between the particles, electrons or magnons, this is known as the diffusive regime. But both for electrons and for magnons, in fact, also for phonon, for every type of excitation, there is a different regime, a hydrodynamic regime, where the rate of collisions between particles is much faster than that of the rate of loss of momentum or energy in the system. So if you think about individual particles, they don't conserve energy or momentum. But in this limit, on average, they're just moving momentum and energy between the particles. The collective maintains energy and momentum, so there are conservation laws that govern the behavior of this system. And it turns out that if the magnons are in this system, these fluctuations of number of magnons become a long-lived mode. In fact, it becomes an acoustic mode, and it's actually the second sound. So in the limit where the number of these particles is large, it's coming from somewhere. It's on account of having my condensed phase, my magnetization, be a little bit smaller. And whereas when the number of excitations is small, it means that my ordered phase is large. This is precisely what happens in liquid helium. That is second sound liquid helium. These are temperature variations in the system. Here the temperature is high. I have a lot of excitations and magnetization is small. Here temperature is low. Small number of excitations, magnetization is high. And this thing is a coherent mode now that propagates across the sample. And here is a dispersion, the susceptibility of this mode as calculated by our collaborators, Eugene Demler and collaborators over at ETH. And you see that as we pull down to low energy and low momentum, this mode becomes narrow and well-defined. And as you can see at high energy, high momentum, it is very broad, and that has to do with the viscosity of the system. Yeah.
So should I think of that as bulk viscosity, as a transverse viscosity, or as scattering?
You should think of this as viscosity. I need to think whether it's, I mean, you can think of it as transverse viscosity. Basically, if I have a magnon that's moving fast, it's going to drag itself, it's going to drag another magnon. And so just like this, there's nothing different from electrons or viscosity in air, if you like. It's what dampens the motion of sound waves in air. It's viscosity of the it's bulk viscosity. Yeah. But this is 2D, but yeah, it's bulk. I'm not going to show explicitly why, but it turns out that the imaginary part of this susceptibility is proportional to the viscosity. And if you follow how the viscosity depends on various parameters in the system, actually ends up going as 1 over temperature. And this is really important. Again, note that people, this is Dyson Freeman, who's already in 56, yeah, calculated the viscosity of magnons. So, you know, very old topic, but unfortunately, we're only today being able to kind of try and start probing some of these quantities. And so it's this 1 over temperature that's really important, that's going to explain why we are seeing more noise at lower temperature. So this is at some temperature, 6 Kelvin, you see the dispersion here. And note what happens when you go to a higher temperature. At a higher temperature, viscosity becomes smaller. So this mode becomes better and well-defined. And you see that since we're probing noise at very low frequency and a certain momentum, 1 over 50 nanometers, you see that we're probing really the tail of this mode. And when we go to higher temperature, we see that there is much less noise where we're probing. If we were able to probe directly at the frequency of this second sound mode, we should see a clear peak, and that's what's coming next. But this really explained to us why, for some reason, as we cool the system down, we get more noise because it's becoming more and more viscous. The sound mode is becoming more and more viscous. And using our theorists' collaborators, we could derive the dependence of this viscosity on a variety of system parameters, and you can see we can really fit nicely the dependence of the coherence with temperature based on very few system parameters, and we extract its viscosity, which is actually very, very high. So this is a very, very viscous fluid. Now, we were curious now. We said, okay, so we're starting to understand what's going on in the system. What about a multilayer? And as I mentioned, a multilayer system is antiferromagnetically. But the magnons that govern this second sound, remember, it's fluctuations of the number of magnons, but the magnons themselves, they're very high frequency magnons, and they are populated by just temperature, because of temperature. The wavelength of these thermal magnons is smaller than the distance between layers. So whereas the static phase is very much correlated between the two layers, the fluctuations of each layer is decoupled. So by going to a multilayer, we should just be able to see a bigger signature of the same effect. And in fact, that's what you see. You can see that indeed noise, again, does not go down as you cool the system down. Obviously, eventually, if we cool down to 0 temperature, things will quiet down, but that happens at much, much lower temperatures, and the physics of a multi-layer is very much the same as that of a single layer. But we wanted to really see the mode. So we started devising a slightly different variant of our experiment, and instead of just doing the echo experiment to measure the coherence, what we're doing now is we're driving the system during our sensing period. And what we're trying to do is we're trying to see, okay, can we drive it at this frequency? Can we drive it here? Can we drive it here? Shouldn't we see more noise when we drive it on resonance than off resonance? And we've done a lot. So just to show you that this is no drive, that's the dependence, the coherence time of the NV as a function of its evolution time. And you see that once we drive, we have a far lower coherence. So we're clearly exciting the system, but let's see how effective are we in exciting the system depending on what frequency we choose. We've done a lot of calibration here, you see, just to convince ourselves that nothing happens over the bare diamond and a lot happens over the material. I won't bore you with the details, but it's really all coming from the material itself. And here you can see the frequency dependence, and what you see is a very clear resonance appearing at roughly 300 megahertz. It's a little bit lower than what our theory friends tells us, but it's not that surprising because there are many unknowns that are hard to determine. But you can now very clearly see that our ability to excite the system and drive it strongly depends on what frequency we choose. And when we choose the correct frequency, we see a lot of fluctuations in the system. So this is directly driving the second sound mode and a direct spectroscopic observation of it. Note that there is a very strong signature also at low frequency. We call it a Lorentzian. We don't really have a good understanding of what this is coming from. You can also ask, how are we driving the system? Well, in fact, we're driving it with a uniform magnetic field, but the sound mode has a very short wavelength. So how is it that we can drive the system by a uniform magnetic field? Note, this is the strength of the response of our NV centers over the flake. And you see that the boundaries are highlighted. And what this means is that the boundaries is what breaks translational symmetry that drives the mode at the frequency that we're driving. Lastly, there has been a lot of developments in the theory that is trying to explain this. And note, the theory does produce a rise at low frequency. It has to do with the details of how the NV is probing and the various singularities in the system, but we are so far unable to fit this model to the data. So that's why I'm showing it separately. This rise is much, much steeper in theory than what we're seeing in experiment, and we believe that it's coming from a different origin. And lastly, we can, of course, do a temperature dependence and see indeed how the viscosity is changing in the system. And what you can indeed see is that the viscosity, which is the width of the mode here, is changing as you change temperature, and it's becoming narrower and narrower as you warm the system up, just like we expect the viscosity of the system to do. All right, so with this, just short conclusions. So, we are developing new probes and really targeting new materials and trying to understand and extract new physics using these sensing techniques. Here, what I've been able to show is that we can measure directly chemical potential. There are interesting developments in the community that now take these kind of techniques and measure gradients of chemical potential, and together with techniques to measure spin currents that use inverse spin Hall effect, for example, are able to extract spin conductance in various materials. And then this is really exciting for us, the measurement of second sound. I think there's much more to do here. We're just kind of starting and scraping the surface. Thank you.
Okay, Jake.
Kind of a dumb question, but what happened to the first sound? Like, isn't there usually the theory of second sound in helium you have a two fluid model that you mentioned, one superfluid and the other. But maybe I missed the superfluid. So
first sound, okay, so for each component, there would be a first, so, the ferromagnetic resonance, for example, the spin excitations are the first sound of the magnet. These are basically the first sound. So in a system that's very isotropic, they will form a sound mode, and they would be linearly dispersing. Their speed is about 1,000 meters per second. They're really fast. This is a much, much slower mode, maybe 50 meters per second. But
of that mode.
oh yeah, I mean, direct measurement of spin waves, and I'll show tomorrow, I think, some real visualization of coherent spin waves for sound, if you like, in magnets. Yeah.
So I think you showed this 2D sheet of magnets. They don't produce any magnetic field. And I think in one of the earlier experiments, like the slide you showed, the 2D flakes, actually the ND imaging, you can see the magnetization of the 2D.
So you can see it at the boundary.
Somehow you see the inside the bulk, like there's a.
You can see some variations. So okay, if you remember my filter function as a function of momentum, it goes to 0 for k equals 0. It's exponentially small for large k, and it peaks at k equals 1 over d. Its rise from k equals 0 is linear. So if you think about a response in momentum space that is linearly dependent on k, it basically tells us that what our sensor probes are gradients of magnetization, because it goes linear in k. So this is what we're picking up. Anytime your bulk magnetization is going to change, once there's a change in magnetization, that's where we can pick it up. When it's uniform, we can't.
It's not obvious how a microwave drive can couple to fluctuations in the number of magnons and, be able to make up the energy gap. Can you comment on what that mechanism is? Like, how do these things actually couple?
It's a good question. We have not thought about that in detail on what's the mechanism. What I'm suspecting is that, number one, we're not at 0 temperature and the magnetization is not saturated. So when you're oscillating the magnetic field, what happens is that you are increasing the magnetization, and maybe on account of that, decreasing the number of fluctuations. Also remember that your magnetic field is controlling the spin gap in the system. So as you're oscillating that, you are modulating the number of spin excitations at any given energy. But we haven't really kind of worked that out in detail to think how the microscopics works.
This question, like, does this resonance have any impact on relaxation or relaxometry? Like, is it possible to pick it up? I assume this is like phasing.
So yes, I mean, if you had a method that could measure the fluctuation of the magnet in equilibrium at this frequency and this wavelength, or you could do it really spectroscopically in thermal equilibrium, right? Here, we're measuring this window, and we're just seeing what happens when we drive at these different frequencies. But at the end of the day, we're always sensing fluctuations at low frequencies and this wavelength. There are techniques like driven echo that allow you to, again, control this filter function and frequency to various frequencies. The problem with all these techniques is that they use a lot of drive, and the drive will excite the magnet. So how to devise a technique that is kind of just spectroscopic and not driving the system, and yet allows you to choose what frequency and what wavelength you're measuring is a challenge, but it's a good challenge to solve.
Jay and Aki, those are the last questions.
So what would it take to measure the really sharp feature at low wave? Yeah.
We're working on that. So obviously, yes, obviously you see that the further away you are, the longer the wavelength you're going to probe. So we're going to be pushing down. The problem with being further away is your signals become small. But that's the direction we're headed. We're trying to see how far we can go to longer and longer wavelengths.
But alluding to something at the beginning, as having multiple NBs can you leverage that somehow?
Yes, so the other thing you can try to do is basically launch, right? So we're trying also to do some spatial dependence. So here, this mode should really propagate over long distances. So if you could excite it here and see how long it took the fluctuation to arrive at a different point, you should also be able to extract the velocity, for example. Yeah.
How do you park your NV sensor like 15 nanometers away from the sample surface?
It's done using similar, so it's mounted on a tuning fork. So it's very similar techniques that you use for atomic force microscopy. We're basically measuring the force between the tip and the sample. And this is one way. Another way is our sensors are actually multiple pillars rather than one. And what we do is we'd rest one directly on the surface and we'd tilt the others to be at a desired distance from the sample. So this way we're not hovering, we're really in contact somewhere far away from the sample, and we're having a different pillar that is being used to probe at a different location.
Okay, well, thank you.
Sure.